Hello everyone, this is Ankit Shivare. I am research scholar pursuing my PhD in IIT Kharagpur. In this module 0, we are going to talk on energy bands and charge carriers in semiconductors. Before going into the topic, let us know what are conductors, what are semiconductors and what are insulators. So conductors, semiconductors and insulators. So how to quantify these terms? Semiconductors conductivity lies between insulators and conductors. The resistance of semiconductor also lies between conductors and insulators. Similarly, you can say resistivity of semiconductor also lies between insulators and conductors. Okay. So this is how we can say what is conductor, what is semiconductor and what is insulator. Okay. So conductors are the materials which can conduct electricity very fast. Semiconductors, you need to have some doping, otherwise it behaves almost like an insulator. And insulators are materials like rubber which doesn't conduct electricity. Okay. So this is how we define the terms. Now in semiconductor we split into two categories, that are the intrinsic semiconductors and the extrinsic semiconductor. So like group 4 elements, you can say these are the intrinsic semiconductors. So you know the group 4 elements are carbon, silicon, germanium, tin, lead, right? In this we see silicon and germanium that are used for our work. Okay. So generally we study for semiconductor devices with silicon and germanium. So what is silicon? Silicon, the element number of silicon is 14. So that is what? 1s2, 2s2, 2p6, 3s2, 3p2. Okay. So this is how we write down. Okay. So you can see that at n is equal to 3, there are 4 electrons. Okay. So and at energy state 3, we are having 4 electrons. Okay. So in this case, 4 states are filled and 4 states are vacant, because the total capability of this energy is what? It's 8, right? Because 3s2, 3p6 it could go. So that is 2 plus 6, that is 8 states are possible. So at energy state 3, we have 8 states. Out of that 8 states, 4 states are filled and 4 states are vacant, right? Similarly, for germanium, the atomic number is 32. That is again 1s2, 2s2, 2p6, 3s2, 3p6, then 3d10, 4s2, 4p2. Okay. Okay. Again at energy state 3, you can see there are 8 states possible. There are more than 8 states possible, okay, in this energy state. But for S and P, we can see that there are 8 states, okay. And out of that 8 states, 4 states are filled and 4 states are vacant. So there is possibility that these energy states can be occupied, okay. So at room temperature, the intrinsic carrier concentration of silicon is 1.5 into 10 to the power 10 per centimeter cube. Okay. So this is the intrinsic carrier concentration. What do you mean by this? That these number of electrons are available per centimeter cube at room temperature, that is 300 Kelvin. Okay. So these are the things that are available. Okay. Now the concept of electrons and holes come to the picture. Okay, so what are electrons? Electrons are the, so we know this electrons, holes. Okay, so what are electrons? Electrons are, suppose electrons are having some energy. Okay, and suppose we apply an electric field in this direction, the electrons will have a tendency to move in the opposite direction compared to the electric field. The holes will have a opposite tendency. These are the holes and they have a tendency to follow the electric field. So the question that arises, what are holes? So look, there are in energy states that are available. Okay, like in from Pauli's exclusion principle we can see that at each and every energy state the electrons will have their quantum numbers, right? Like we say sp, d, f. Okay, these are the energy states that are existing. Okay, so at each energy state the energy states are much available, right? Like in S there are two energy states. At P, so at energy state S there are two energy states available, right? At P there are 6 energy states that are available. At D there are 10 energy states that are available, right? At F there are 14 energy states that are available, right? We know these things. These are coming from the Pauli's exclusion principle, then there is spin number, etc. We are not going further on the chemistry. Okay, we are assuming that you know these stuffs, right? So holes have a tendency to move in the electric field. Now how the holes comes to the picture? So suppose there are 4 electrons in the valence band for silicon. Okay, suppose an electron move from one silicon atom, and these are the 4 electrons in the valence band. I am not talking about the other electrons. Okay, these are well occupied. Okay, so suppose this electron moves, and this is silicon. Okay, suppose this electron moves from this energy state to another, to outside. Okay, so this electron has gone. Okay, so this state is unfilled. Okay, so what can happen, that suppose there are many silicon atoms and each has their own valence band. Okay, so and this is having the electrons. Okay, now what happens if suppose you apply electric field, suppose these atoms are tightly packed, the electrons in the valence band will have a tendency to cross this energy barrier and move to the other valence band of silicon. Okay, so what happens when you see, suppose you apply electric field and suppose there is one more silicon atom. Okay, and again the 4 electrons. Okay, and suppose this electron has left. Okay, and you have applied the electric field in this direction. What happens, that this electron will go in this direction, in the opposite direction of electric field. Okay, now since you have applied the electric field, these electrons in the valence band will also have a tendency to move in the opposite direction. Okay, so this electron here, it doesn't have very high energy to leave the silicon atom, but what will it do? It will jump from this energy state to the vacant energy state. Okay, and now this is the vacant state that is available. So this is the vacant state. Now since you have applied the electric field, the electrons at this silicon atom, since it is tightly packed, so this will have a tendency to go to this vacant state. So what you are seeing here, that the electrons are moving in this direction, but suppose you see a bubble analogy. In bubble analogy what happens? Suppose you have a water that is filled. Okay, and suppose it is filled fully. Okay, and you have a bubble in between, right? Suppose this is the bubble that is available to you. Now when you tilt this bubble, what will it go? Suppose you have tilted this glass. Okay, So when you tilt this glass, and again it is filled with water but little bit space left. So when you are tilting it, what you will notice, this bubble, so you are tilting this glass in this direction, okay, you are curving it, okay. So what happens, this bubble will have a tendency to move in this direction, okay. What is actually happening, the water in the downward side will have a tendency to move towards the air, that is the bubble, okay. But what actually we are seeing, that the bubble is moving in this direction, okay. What is actually moving is the water, okay. It is filling the air space in the bubble, okay, and it is moving up. So similarly is the whole concept, okay. The electrons are moving from one vacant state to the other vacant state, okay. They have a tendency to move, okay. But what will we actually observe, that this hole is moving, okay. So it is moving in this direction. So one vacant states are moving, you will see like this, okay. So vacant states you will see, and you will see that this vacant state is moving, okay, like this empty state, okay. So the electrons are moving from this, suppose it is very filled, it is moving to the other and filling this state, and this state is now left behind. So you can say it's open. So this is the bubble analogy you can understand for the holes, okay. In the next module, we will be discussing on the Fermi level energy band diagram. I hope you are clear with the concept of electrons and hole. Thank you.